Hello everyone, we shall start our lecture on formal language automata and codes. And today we have lecture number 10. And our lecture will be devoted to regular grammars. So we should start. A simple way of describing regular languages is by means by certain grammars. Grammars are often an alternative way of specifying languages. Where we define a language family through an automaton or in some other way, we are interested in knowing what kind of grammar we can associate with the family. We look at grammars that generate regular languages, right and left linear grammars. Definition. A grammar, G, said to be right linear of all production of the form A to XB, A to X, where A and B belongs to V and X belong T star, T capital star. A grammar is said to be left linear if all production are of the form A to B X and A to X. A regular grammar is one that either right linear or left linear. And we know that in a regular grammar, at most one variable appear on the right side of any production. Furthermore, that variable must consistently be either the rightmost or leftmost symbol of the right side of any production. Example, a grammar G1, because this is a single set as our alphabet A, B, and S and P1, with P1 given us S into A, B, S capital, or S to A small, is right linear. The grammar G2, which consists of S, S1, S2, yeah, our alphabet A, B, S, P, 2, with production S into S1AB, S1 into S1AB, or S2, yeah, and S2 into A is left linear. Both G1 and G2 are regular grammars. The sequence S into ABS into ABS into ABA is a derivation with the grammar G1. From this single instance, it's easy to conjecture that L of G1 is a language denoted by regular expression R, which is equal A, B, and star A. In a similar way, we can see that L of G2 is a regular language, which is denoted by a regular expression A, B star. Next example. The grammar G, which consists of S, capital A, capital B, capital our alphabet A, B, and SP, with production S into A into A small b, or A into empty word lambda, and B into A capital B, is not regular. Also, every production is either into right linear or left linear form. The grammar itself is neither right linear nor left linear, and therefore is not regular. The grammar is an example of a linear grammar. Linear grammar is a grammar in which at most one variable can be occur on the right side of any production without the restriction of the position of this variable. Clearly, a regular grammar is always linear, but not all linear grammars are regular. Our next goal will be to show that regular grammars are associated with regular languages, and that for every regular language, there is a regular grammar. Thus, regular grammars are another way of talking about regular languages. So, right linear grammars generate regular grammars, languages. First, we show that a language generated by a right linear grammar is always regular. To do so, we construct a non-determinate finite acceptor that mimics the derivation of a right linear grammar. We know that the synthetical form of a right linear grammar have a special form in which there is exactly one variable and it occurs as a rightmost symbol. Suppose now that we have a step in a derivation. So A, B, so on, C, D capital into A, B, so on, C, D, E capital, arrived by the using production D into D, E capital. The corresponding deterministic finite acceptor can imitate this step by going from state D to state E when a symbol D is encountered. In this schema, the state of the automaton corresponds to the variable in the synthetical form, while the part of the string already precedes and is identical to the terminal prefix of the synthetical form. This simple idea is the basic for the following theorem. Let G be a right linear grammar, then L of G is regular grammar, that the language is generated of this grammar is a regular language. Proof. We assume that V capital is equal V0, V1, and so on, that S capital is equal V0, and that we have production of the form V0 into V1, VI, VI into V2, Vj, so on, or Vn into Vl, so on. If W is a string of the LG, of the language which is generated by the grammar G, then because of the form of production, V0 into V1, Vi into V1, V2, Vj, and into star V1, V2, so on, Vk, Vn into V1, V2, so on, Vk, Vl, which is equal W. The automaton to be constructed will be reproduce the derivation of consuming each of these V's in turn. The initial state of the automaton will be labeled V0. And for each variable, we either will be a non-final state labeled by VA, sorry. For each production, VI into a small 1, a small 2, so on, a small m, vj, the automaton will behave transition to correct v I capital and vj capital, but that delta will be defined so that delta star of v capital I a1, a2, so on, am is equal like v capital J. For each production, v capital I into a1, a2, so on, am, the corresponding transition of the automaton will be delta star of v capital I a1, a2, so on, am is equal v capital F, where v capital F is a final state. The intermediate states that are needed to do this are of no concern and can be given arbitrary labels. The general scheme is shown in the following figure. The first figure represents transition, the transition V capital I into A1, A2, so on, AM, VJ. And the second figure represents the transition VI into A1, A2, yeah, so on, AM. The complete automaton is assembled from the such individual parts. Suppose now that W belongs to LG, so that this formula 1 is satisfied. Yeah. It's a deterministic finite acceptor. There is by construction, apart from the state V capital star to the state V capital I labeled by the word V1. Apart from V capital I to the state V capital J labeled by the word V2, and so on. So that really V capital F belongs to delta star of V capital 0 double V. And the word double V is accepted by automaton M capital. Conversely, assume that the word double V is accepted by automaton M capital because of the way in which automat M capital was constructed. To accept the word double V, the automaton has to pass through a sequence of stages. V capital 0, V capital I, so on, to V capital F, using paths labeled by the word V1, V2, and so on. Therefore, the word W must have the form W is equal V1, V2, so on, Vk, Vl, and the derivation V capital 0 into V1, V capital I into V1, V2, V capital J into star V1, V2, so on, Vk, V capital K into V1, V2, so on, VK, VL is possible. Hence, the word W is in the language is generated grammar G, and the theorem is proved. Example. Construct a finite automaton that accepts the language generated by the following grammar. V capital 0 maps into derives into V capital 1, V capital 1 derives AB, V capital 0 or V capital 1 into B, where V capital 0 is the start variable. We start the transition graph with the vertices V capital 0, V capital 1, and V capital F. So first production rule create an H labeled by the symbol A between the states V capital 0 and V capital 1. For the second rule, we need to introduce the additional vertex so that 3 is a path labeled by AB between V capital 1 and V capital 0. Finally, we need to add an edge labeled by the word B between V capital 1 and V capital F, yeah, given the automaton shown in the following figure. The language generated by the grammar and accepted by the automaton is the regular language the following. So this is grammar, this is automaton, the language is the following form. So the AAB in the star and multiply AB. Write linear grammars for regular languages. To show that every regular language can be generated by some right linear grammar, we start from the deterministic finite acceptor for the language and reverse the construction shown in theorem 3.3. The state of the deterministic finite acceptor now become the variable of the grammar, and the symbols calling the transition become the terminals in the productions. Theorem. If L capital is a regular language on the alphabet sigma, then there exists a right linear grammar G capital will generate language L. Proof. Let M be the deterministic finite acceptor that accepts the language L. It consists as the set of states Q, the alphabet sigma, the transition function delta, the initial state Qi, and finite state of final states F capital. We assume that the set of state consists of Q0, Q1, so on, Qn. And the alphabet sigma capital consists of the symbol A1, A2, so on, AM. Construct the right linear grammar G with these it consists of Q0, Q1, so on, Qn, and S consists of Q0. For each transition, delta of Qi Aj is equal Qk of automaton M capital. We put in P capital the production Qi into IJQK. In addition, if the state Qk is in finite in all states, we add to P the following production, qk into empty word lambda. We first show that the grammar G capital defined in this way can be generated everything in the language L. Consider any word W from language N of the form W is equal I, J, so on, AK, AN. For the automaton to accept this stream, it must be make moves via the following. Delta of QI Q0, sorry, AI is equal to QP. Delta of QP AJ is equal to QR, and so on. Delta of QS AK is equal to QT. Delta of QT AL is equal QF belong to final states. F. By construction, the grammar will be one production of each of these deltas. Therefore, we can make the derivation Q0 into AIQP into AJQR into star AI, AJ, AK, QT into AI, AG, AK, AL, QF into AJ, AK, AL. With the grammar G capital with the word W from L of G. Conversely, if the word W belongs to LG, then its derivation might have the following form, yeah? But this implies that delta star of Q 0 AI, AG, so on, AK, AL is equal to QF, completing the proof. For the proposed constructing of the grammar, it is useful to know that the restriction that automaton be a deterministic finite automaton is not central to the proof of theorem 3.4. With the minor modification, the same construction will be used if automaton and capital is a deterministic finite acceptor. Example. Construct a right linear grammar for the language, the following language. L of A B star A, the transition function for an deterministic finite acceptor together with the corresponding grammar production is given in the following figure. Transition, yeah. The result was obtained by simply following the construction in theorem 3.4. The string ABA can be derived with the constructed grammar by the following transition Q0 into AQ1 into AAQ2 into AABQ2 into AAB AQF into AABA. Equivalence of regular languages and regular grammars. The previous two theorems establish a connection between regular languages and right linear grammars. One can make a similar connection between regular languages and left linear grammars, thereby showing the complete equivalence of regular grammars and regular languages. Theorem. A language L capital is regular if and only if there exists a left linear grammar G capital such that L is generated by this grammar. Proof. We only outline the main idea. Given any left linear grammar with the production of the form A into B capital V or A capital into V, we construct from it a right linear grammar J capital with head by replacing every such production of the grammar G capital with the following transition. A capital into reverse world of VB or A into reverse of word of V respectively. A few examples will make it clear quickly that um, L of G coincide with reverse words of L of G hat. Next, we use the fact which tell us that the reverse of any regular language is also regular. Since the grammar G capital with hat is right linear, then L of G capital head is regular, but then so are was reverse word of L of G capital with head and L of G. This complete the schema proof. Putting in theorems 3.4 and 3.5 together, we arrive at the equivalence of regular languages as regular grammars. Theorem. Language L capital is regular if and only if there exists a regular grammar G capital such that L is equal L of G. We now have several ways of describing regular languages: deterministic finite acceptors, non-deterministic finite acceptor, regular expressions, and regular grammars. While in some instances one or the other of these may be most suitable, they are all equally powerful. Each gives a complete and ambiguous definition of a regular language. The connection between all these concepts is established by the four theorems in this lecture, as shown in the following figure. Yeah. So regular grammars, deterministic finite acceptor or non-deterministic finite acceptor, and it's equivalent that this automata by theorem C1 and C2 determines so languages, so regular expressions here, and by theorem 3.4, it's equivalent that this language determines deterministic finite acceptor or deterministic finite acceptors. So we finish our lecture. Thank you for your attention. I wish you good luck, good health, and finish this Russian war. Also, I ask you send me mail that you listen my lecture. Thank you. Goodbye. Good luck.